This is the Riemann hypothesis, one of the most difficult problems. Even understanding the question itself is not easy. And yet, the message it reveals about prime numbers is surprisingly simple and unexpectedly beautiful. Which of these looks like the distribution of prime numbers? That's it. Let me show you what it's really saying. And let's reduce the Riemann hypothesis to a single sentence anyone can understand. Up to 10, there are 4 prime numbers. Up to 100, there are 25. So then, how many primes are there up to 1000? This simple question leads directly to the Riemann hypothesis. But don't be too quick to think this hypothesis is just about counting primes. It goes far beyond that. At first glance, prime numbers seem completely random. In some regions, they cluster together. In others, they are far apart. Individually, they feel unpredictable. But something strange happens. If we look at the number of primes less than x, a clear pattern begins to emerge. Numbers that seem random up close begin to reveal structure at a larger scale. So, mathematicians began searching for a way to capture this pattern with a single formula. Remarkably, Gauss proposed one, Li of x, a simple function that approximates how many primes there should be. Compare the actual count pi of x with Gauss's prediction Li of x. As x grows larger, the gap between them also grows. However, the ratio between them approaches 1. They become closer and closer, but there's always an error we can't ignore. So, where does this error come from? One mathematician took this question further. His name was, as you guess, Bernard Riemann. Riemann didn't stop at approximation. He asked a more fundamental question. Is there a hidden structure behind this seemingly random distribution? Then, instead of studying primes directly, he turned to a completely different world. A function defined over complex numbers. In particular, he focused on a special set of complex numbers associated with that function, those that satisfy very precise conditions. And what he discovered was astonishing. The fine structure of prime numbers is encoded in them. The secret of primes is not just hidden among natural numbers, but deep within the world of complex numbers. After seeing the pattern of those complex numbers, Riemann then made a bold claim. They all seem to share one striking property. Their real part is exactly 1/2. All of them lie on a single vertical line. This is the Riemann hypothesis. But here's the surprising part. In fact, there are infinitely many of these numbers. And yet, Riemann knew only a few, 3 to 6. And still, he made this claim. If this hypothesis is true, then the number of primes can be predicted with astonishing accuracy. These ratios steadily decrease, approaching 1. Primes are not completely random. They follow a deeply structured pattern. But if the hypothesis is false, then unexpected patterns could emerge, far beyond our predictions. These ratios converge to 1 overall, but they can certainly spike or drop along the way. We might find massive clusters of primes in some regions, while others remain almost completely empty. So, what kind of randomness do primes really follow? Are they spread out evenly at random? Or do they form clusters and gaps? or something in between? The Riemann hypothesis is, at its heart, a statement about the nature of that randomness, about how orderly the distribution of prime numbers truly is. Wanna go deeper into this mystery? Stay with us. We'll follow Riemann's path step by step and uncover this mystery.